Hi, this is Pankaj Kumar. In the previous video, I have explained you about the layout of Hyperworks. So now in this video, I will explain you the products from the LTR in Hyperworks and the methods on which the software mainly works. So there is a list of the different software modules that comes under the Hyperworks developed by the Altair Engineering. So there is a OptiStruct, which is a structural analysis solver. It means this one is for the linear and non-linear both the problems, and this one is a optimization tool. By using the OptiStruct, you can solve your linear and non-linear problem, and can do the different type of optimization or mass reduction reducing processes. And the other one solver is the Radios. This one is highly non-linear problems solving solver, mainly used for the dynamic loadings. Uh, this one is mainly used in the automotive crash and impact analysis. And the third one is my motion view. Motion view is a multi-body preprocessor. The solver file for the multi-body solver is first generated or pre-processed in this motion view module, and then after the creating the solver DAC for the motion solve, that one problem is solved by the motion solver, which is the multi-body solver, and integrated solution to analyze and optimize the multi-body system performance. The other one software module is hyper extrude for the metal and polymer extrusion solver. This one is the advanced solver for manufacturing related problems, and simulation and their validations. And here is my hyperform, which is a metal forming solver. There is other tools for CAE pre and post processing like Hypermesh, Hypercrash, SimLab, Hyperview, Hypergraph. Hyperstudy is for design of experiment and multidisciplinary design optimization. Hypermath is for mathematical analysis environment in which we can solve our problems in a mathematical environment. And the third one is and the next one is my AccuSolve, which is for CFD or finite element based CFD solvers. When you go through the other CFD solvers, they might be finite volume based or finite boundary based, but this one solver is finite element based, and this one is more robust than the other solvers. And there is my other 3D electromagnetic solver as FACO. So now we have to know about what is the need of CAE and FEA, why we work on them. We may work without considering the CAE and finite element methods or finite element analysis. So the reason behind that is this that in the traditional design processes, we first design our product and then make virtual tests. We build them and then test. After this, we again modify that one component to optimize our component by reducing the weight or changing its shape and size. And by this, the loop is going on up to which we will get a fully optimized component. This one process is very costly, and this one process take a lot of time, and a lot of money is needed for to fulfill this redesign loop. So the component that is generated will be more costly. So to reduce the cost of this redesign loop, a new loop is given by Altair design approach, in which we optimize our CAD model or the our design by the after just after the virtual test before and after optimizing our component in the virtual test, we go for manufacture for the prototype building, and then test and validate that one component. So this one process becomes less time consuming and more cheaper than the real redesign loop. So this one approach is mainly followed in many industries all over the world. So the approach designed by Altair is more beneficial for creating the industrial products. So now we go for how the software solve the problem or the methods that are adopted by the software. There might be three methods for solving the problem. It may be analytical, practical, and numerical. In case of analytical, we mainly focuses on the some mathematical formulas. This one is uh, accurate, but and there is no need of approximation in analytical method. But this one method is limited to simple problems only. Complex problems are not solved by this one method. And the second one is practical method. This one is practical approach in which we test our component and practically, and the datas are used. This one is also limited to the simple structurals, and the data we will get from the practical method is not too much beneficial, because the practical method is only used to validate our results. And the third one is the numerical method. Numerical method are the methods which are based on numerical calculations. The software uses the numerical method in which the problem is discretized or broken into the small elements, and the connecting nodes or connecting points are considered under the calculation, and the mathematical modeling is done. And the equation formed by that mathematical modeling are solved by numerical methods, and the result is post processed. So the numerical method is somehow is more useful over these one, but there is a drawback of numerical method, which is that we approximate in numerical method, because in a numerical method we didn't consider the atom or atomic forces. We break down the whole component into small elements, and then do the calculations over the nodes. So this one is the approximated data. The numerical method on which the hyperworks mainly work is the FEM, or finite element method. So there is a meaning of finite element and method. Finite means that something is made from infinite to the finite, which one I will explain later. And here the E stand for element. The element is because my component is broken down into small elements. And the M stand for the method, means that the whole process the of solving this one problem is just a method. It means a finite element method. Here is other what is that? FEA, finite element analysis. Why FEA and how it differ from FEA? Uh, FEM is the application of FEM, as we can say that in the childhood we mainly learn how to calculate. we do the calculation on our hands and do the small multiplication, division, uh, addition and subtraction on the copies. That one is a method, that how we do the calculation, how we generate the data. And now we are using these the calculations from the childhood to the real life, which one is the use. So in this method, the problems are solved through the finite element method. And the use of the FEM is the finite element analysis. In finite element analysis, the CA engineer mainly works over the problems and create the results on which the component is optimized and is studied for the whole performance of the component in its life cycle. So now I go for the degree of freedom. What is degree of freedom? Uh, as I have explained in the video, what is degree of freedom? Here you can see that there is a infinite number of points in a component. So the degree of freedom and the degree of freedom per point is 6. So the total equation will be infinite number of equation. And if we discretize that one product, so my number of nodes will be 8, and the total equation will be 48 because the degree of freedom per node is 6. So by this my infinite number of equation or degree of or the total degree of freedoms are discretized, and they are reduced to finite number of degree of freedom. And the degree of freedom concept can easily be understand or visualized by considering this component. This one is my coordinate system, and this is my component. And now I will show you how, what does it mean by 6 degree of freedom. This one is my component, and uh, uh, this component is moving related to this one coordinate system. So my this component can translate about the or along the x-axis. So this one will be my first degree of freedom. And this one is my, now my component is moving along the y-axis. So this one is my second degree of freedom, means translational about y direction, or DOF2. And my component can now easily be translated in z direction, which is my degree of freedom 3. So these three are my translational degree of freedom, and the other 3 degree of freedom are the rotational degree of freedoms. So this one is my rotation about y, rot y, or you can say that DOF 5. If this component is rotating about x direction, so this one will be my DOF 4, or rot x, so rotation about x. This may be rot z, rotation about z, or DOF 6. So this one is my degree of freedom. And in real life, each component have a set of degree freedom, which are constrained by applying the joints or constraint points. As you can see that in the door, the door is constrained by the revolute joint, in which the only available uh, degree of freedom is rotation about the axis of the revolute joint. Hello. So after the discretization, the total degree of freedom or the total number of equations are decreased to finite number of equations. So software uses a different type of approach, because in real life the component is made of the small atoms. But while we considering the FEM or solving with the numerical equation. The whole domain is discretized into the smaller units, that is the elements, and the connectivity are defined as the nodes. So here you can see and the difference between both the approaches. Here the one is a continuous approach where all the real life components are continuous, and the other one is a discrete approach or equivalent mathematical modeling. Discrete mathematical equivalent model. So in the both two pictures, the same problem is defined. Here you can see that a child is sitting over their table, and the weight of the child is normal downward on the table. So this one is the discontinuous approach, in which the mass of each atom is considered, and the whole load is distributed over the uh, atoms on the upper surface of this one surface, and which are supported by their nearby atoms, and this one whole cover the atoms and molecule. So this one is a continuous approach. If we will go to solve the equations for all these small atoms, it will be take infinite time to solve a small problem. So the approach used for numerical equation or numerical modeling or mathematical modeling is a discrete approach, in which my problem this one same problem is discretized, and here the mass of this child is concentrated over a node, and the forces are distributed by the rigid element on the nodes, and the legs of this table is considered as a 1D element, and the upper surface or the seat is matched with the 2D element. So here there is a limited number of elements on which the analysis will done, and the values will be calculated for its mm, all the real life problem or the worst problem that will be acted upon this component. And thank you. The steps to solve FEM problem is as shown in this figure. Basically there is three steps. One is pre-processing or modeling, then second is solution and analysis, and the third is visualization and post-processing. So the hypermesh is the pre-processing, OptiStruct and Radios are the solvers, and there is 3 Hyperview and Hypergraph and Hypergraph 3D. These are the post processor. So these three, there is three basic processes uh, by which we have to solve our FEM problem. So first we will start with the pre-processing. In pre-processing, we have to import our CAD geometry and do some geometry cleanup and simplification, because when geometry is imported from the CAD software into any FEM software, there may be some defeaturing due to import, because the file that are importing have different file extension or different file formats. So if there is any defeaturing or simplification is needed to carry out the meshing or FEM, we have to simplify that one geometry file. And then after the simplification and geometry cleanup, the geometry will be ready for the meshing. So now we will have to start with the meshing, in which there is three type of meshing: 1D, 2D, 3D. These three type of meshing are different depending upon the dimension, and all these three are used according to the uh, component or the type of analysis you want. If I want to do analysis on the tubular frame of any like a Supra, a Baja and FSA vehicle, then I may go to 1D analysis of that one frame. I can do also 2D analysis of the frame of the same car, but it will take a little bit time. So depending upon the time and the quality and the geometry type, you have to select which type of mesh you will do. And then we have to move for the quality and compatibility of the mesh. Quality is the main factor while you are going for any finite element analysis, because the uh, calculations done for the analysis are depend upon the coordinate system of the elements. If the quality of the elements will be poor, then your result might be worst or may not be usable for the analysis. The result might be quite wrong. So it is also always advisable that for an analysis, or before proceeding to an analysis, you have to check your elements for the quality check. Then after the meshing, we have to define the material property and solver information, like the output request and others. So after the meshing, these are the parameters that should be provided for the solver, so that the calculation can easily be done, and the output file may be created by the solver. And then we have to define the boundary conditions. After the definition of all the solver information, we have to apply the boundary condition. The boundary condition contains the information for the component, like how the component will behave in the real life or real time situations. In this, we have to consider the worst condition, because if the component may go through the various type of fluctuation loading or a different type of boundary condition, so we have to consider for the worst condition. Then we have to export the FEM deck or the solver deck for the uh, solver to solve. We have to export the FEM deck. Then after exporting the FEM deck, we have to move further for the solver. So to solve the FEM file, simply we run the solver, and the solver start to calculate or compute the all numerical equation that are generated for the finite element method deck. Then after solving, the input file is created, which is visualized or post processed by any post processing software. The output file from the solver are in different formats, depending upon which type of file output request you have assigned to the solver deck. So post processing, software computes all the values that you need. Like if you have applied the load and constrained any component, then you may get the how much type of deflection you have got in your component, or how much stress your component is facing with the loading you have defined. So by this the all FEM processes are carried out while you are going through any finite element method or finite element analysis. And thank you. अब इनको अटैच करो.